Good evening, or good afternoon, everyone. So SION, just to start, is the South African Environmental Observation Network, and I am working there for the year. I'm an intern there, and I'm going to be looking at climate change and its impact on the potential impacts on the geographical extent of C3 grassland in the KZN Drakensberg. It's a joint project with me and Prof. Tim O'Connor. Yeah. Okay, so just to start with a bit of context to the talk. Obviously, the Drakensberg, as we know, is a montane area, and therefore, over a very small region, it has vast ranges in temperature, vast ranges in rainfall, vast ranges in altitude, and related to that is differences in vegetation covering the Drakensberg Mountains. So to introduce the topic, obviously climate change is a big buzzword at the moment, and it's predicted to have impacts on climate as well as biodiversity. We're looking at potential poleward and upslope migrations, possible temperature increases greater than 2 degrees globally, as well as current predictions are showing rainfall decline in South Africa's southwest with uncertainty over the eastern interior. The point is basically these changes are all coming into effect because of a changing climate. And one of the major culprits for these impacts is an increase in carbon dioxide. So further introduction, as we all know, well, I think most of us know, global vegetation photosynthesizes using 3 main photosynthetic pathways, being C3, C4, and CAM. And the climate of an area is one of the determiners for which photosynthetic pathways are the most successful. So in terms of what is known about the ecophysiology of those different pathways, a future warmer climate should favor C4s, and therefore with warming they should move upslope, with the C3s, which favor a cooler climate, having a declining extent. However, in contrast to this, Bond and Midgley did research in 2000 which looked at a mechanism for bush encroachment, and they found that a higher CO2 concentration or increasing CO2 concentrations favors C3 species. And this happens through a mechanism of underground biomass storage and escape from the fire trap. And you can see in the image there, at future CO2 levels, you're looking at a quicker movement to the escape height versus past CO2 levels. It's quite a well-known paper. So in terms of the Drakensberg context, we have potentially something similar happening in that it's a burnt ecosystem, and there could potentially be a similar response. If you look, this is recently burnt grassland, and the Festuca costata are far larger, or have grown a lot more than the surrounding C4s, and Festuca costata is obviously a C3. So potentially a similar sort of response to what you see in our savanna ecosystems. So the motivation for this is that an increase in the extent of C3 grasslands in the Berg, or decrease, whichever way it happens, C3 grasslands will change fundamentally a few things such as freshwater provision, a greater coverage of C3 grasslands. They are evergreen, and therefore could be expected to transpire more, and you'd be likely to have less runoff from these ecosystems, less water runoff, and obviously the Drakensberg is a very important provider of water. Possibly also declined fire spread, and related to that, woody encroachment, which could potentially further decline the amount of runoff from these ecosystems. Also a drop in species diversity from C3 encroachment. These C3 stands which encroach could possibly shade out the surrounding C4s, which are more species diverse, and they cannot compete. We're also looking at possible decline in quantity and quality of mammal forage as well. So our main aim, we are looking at two possible contrasting responses of C3 grasslands in the Berg. Warming could potentially drive the C3's upslope, whereas CO2 fertilization through the mechanism shown by Bond and Midgley could cause CO2 fertilization, which could drive them downslope. So we think that C3s with a temperature-controlled environmental niche suggests the possibility or acts as a proxy for potential future upslope migration and vice versa. So the question is, are their distributions temperature-controlled? And we intend to do this with environmental niche modeling or species distribution modeling, using correlative species distribution modeling, and 6 common C3 species in the Berg. So the study area, I'm sure most of you know the Berg quite well. It has a climate of wet summers with dry, cold winters. Obviously the High Berg consists of basalt, igneous rock, with the Little Berg or the lower reaches of the range made up of sedimentary layers. And in terms of geomorphology, basically it's quite similar throughout the range. It's a bunch of spurs which lead up to the escarpment wall, which forms the High Berg. The sort of predominant type, vegetation type, is a subclimax grassland, where from about 2,000 to just under 3,000 meters, and that covers most of sort of the study area. And the study area we're looking at is between 1,400 and 3,100 meters. That's where I did all my sampling. And I've been doing sampling from the southern Drakensberg at Bushman's Neck all the way up to Royal Natal. And that sampling is still in process, or in progress. It's not quite complete yet. The species we're looking at are these 6: Tenaxia stricta, Distica, Festuca custata, Merksmiller, McCowney, Drakensbergensis, and Stereophila. They're all quite common C3 species throughout the Berg. So far, well, for the purposes of this talk, this is where I have sampled so far, and there are still obviously areas that need to be covered, and that's still in the process of being done. But basically, the way we did it was we took GPS points. We are taking GPS points throughout the range, and they're strategically taken to cover the range in latitude, altitude, and topography. And generally, it's a point taken and then a 3-meter radius around the point looked at to look at percentage cover of the different pertinent species we're looking for. So these are preliminary methods. I did a preliminary, because obviously we're looking at an environmental niche model for these 6 different species. So I did a preliminary, we looked at a preliminary method of doing this modeling, and it's a method I've used in the past for my MSc. So obviously ensemble or distribution modeling relates presence and absence points to environmental predictors, and it tries to determine an environmental niche using that. We have initially tried using an ensemble distribution modeling approach with the algorithms are listed there, small, and those are based on what's suggested in the literature. We have used predictors such as aspect, altitude, and solar irradiance for now. And we use these as surrogates for environmental variables in particular, to try and determine this niche, because they're at a much finer spatial resolution. Environmental variables in the Berg, particularly temperature variables, are not nearly as fine, and not nearly as fine scale. The evaluation was done, and this is classic evaluation, done for environmental niche models, and was done using AUC score, TSS score, sensitivity and specificity. Basically, the way ensemble modeling works is it only takes models which perform pretty well, so models which have an AUC score of over 0.8. So all of these models show an AUC score over 0.8, because that's what is included in the ensemble model. It doesn't include poor models. However, one that stands out for Festuca custata, was shown to be relatively, particularly the specificity number was relatively low, because it's a very common species, very ubiquitous, and therefore, in order for a distribution model or an environmental niche model to be predicted, the model likes a very defined environmental niche. And with Festuca costata being so ubiquitous, it struggles to work out a defined environmental niche because it's all over the place. So that one was shown to have a slightly poorer performance. And you can see that here. So as I said, these are preliminary models we've done so far. But it's a very broad environmental niche model, probably too broad for our liking. Drakensbergensis is also very broad. It's picked up that it's a high altitude species, but also very broad, covering Lesotho and the Heiberg. Makawani it's picked up that it's a low altitude species, but also a very broad distribution model. Merxmiller stereophylla, also a high altitude species, so we'd expect it to be high. Tenaxia distica, quite similar to Festuca costata, but it has picked up more on the south-facing slope than on the north-facing slope, which is what we expect from C3 species. And then Tenaxia stricta has picked up very much on the south-facing slope, but the model hasn't picked up an altitudinally defined potential distribution. So this is a first impression, an initial method, and there does seem to be some temperature control over C3 species, but the models are extremely broad right now, and these models need to be refined a lot and interrogated in order to try and sharpen them or get them to produce a much tighter environmental niche. Right now they are a bit too broad. But basically the research is trying to, as I've stated already, the direction of the research, I think you can see, is trying to look at basically what's going to happen with the future land cover of the Berg, particularly in terms of C3 versus C4 grasslands, because of how important it is for things like freshwater provision, things like biodiversity in the Berg, and mammal forage, etc. And I'd just like to acknowledge my supervisor, and then other colleagues for help in the field, and then Sue van Rensburg for help coordinating. Thank you.